This is Theory of Change. I'm Matthew Sheffield. Thanks for joining me. 100 years after quantum mechanics was born, physics is still living with its consequences. Since Heisenberg and Schrödinger, the theory has transformed science and technology, explaining atomic structure and enabled much of the modern world. But its successes have not erased a deeper puzzle, and that is how the quantum world relates to the classical one that we experience every day. Quantum theory is notorious for its weirdness, which really does make sense. The ideas of superposition, measurement effects, and uncertainty are real, but they have been very often repackaged into quantum woo that labels superstitions as profound scientific facts. But despite the mystical nonsense, though, understanding how classical and quantum systems interact remains the biggest challenge of the physical sciences. But as my guest on today's show talks about in his new book, some of those difficulties are caused by the famous Copenhagen interpretation of quantum physics, which can overstate the role of the observer in quantum measurement and also understate the continuity of quantum dynamics. On this account, reality is quantum all the way down, and what we call objects are actually stable processes, not ultimate building blocks. Vlatko Vedral is a professor of quantum information science at Oxford University, and he's out now with a book talking about all of this and much more called Portals to a New Reality: Five Pathways to the Future of Physics. I hope you'll enjoy. Theory of Change is part of the Flux Media Network, so go to flux.community for more podcasts and articles about politics, media, science, and technology, and how they all intersect and create our culture. And if you like what we're doing, you can subscribe to the show on your favorite podcast app, or you can become a paid or free subscriber on Patreon or on Substack. Just go to patreon.com/discoverflux or go to flux.community. Thanks a lot for your support. And if you're watching on YouTube, please click the like and subscribe button so you can get notified whenever there's a new episode. All right, let's get into the program. And joining me now is Vlatko Vedral. Hey, Vlatko, welcome to the show.
Thank you very much, Matt.
Okay, great. So normally we don't cover physics on the show too much, I would say. But this is what you're doing here is really important, I think, in a lot of ways because, the Schrödinger equation is 100 years old now. And essentially what you're trying to do is to say that, and we'll get into the details more specifically, but just generically, would you say that you're trying to say that what people conceive of as classical mechanics and quantum mechanics, they're not in conflict the way that a lot of people often think?
Yes, I think so. I think you hear all sorts of statements. I think it's a very nice summary of the spirit of most of my writing. Of course, quantum mechanics was a big revolution, and it surprised many people at that time. But if you look at it in terms of how big a departure this is from classical mechanics, then it's very similar to the past revolutions that we had. So certainly you can recover all of the classical ideas in a very special limiting case. And the two theories, so quantum mechanics in that sense can reproduce the classical world. And if you see it like that, you see that there is a continuity going through all of these theories as they develop in the history of physics.
Yeah, exactly. And we'll get further into that as we go along here. But so just to do a little bit basic table setting here, I think probably the biggest maybe difference from how people conceive of chemistry or classical mechanics is that quantum objects are not like little tiny billiard balls.
Yes.
They are processes of things that exist in a flux, if you will. But can you just kind of explain that a little bit better than I did just there?
Yes, I think that's the key feature, actually. The technical word is the superposition principle, which actually states that any quantum object, any quantum particle, like an electron or an atom. And we've tested it with much bigger objects than that in the last 100 years, can actually exist in many different states at the same time. So if you're thinking about an electron, it could exist within an atom closer to the nucleus of the atom and further away from the nucleus simultaneously. And that's called a quantum superposition. And that's, of course, something that doesn't have any analog in classical mechanics, because in classical mechanics, objects have well-defined positions. They are localized. They're either here or there, but not simultaneously in two positions. And the same with all other properties. If they have an energy, they have a well-defined energy, they have a well-defined velocity, motion is well-defined. Whereas in quantum mechanics, it seems that you have to acknowledge that actually we need to deal with probabilities at the fundamental level. So we can never say for sure where particles are unless we make a measurement to confirm where they are. But even then, very quickly after the measurement, the particle will spread across the space and will assume this state of superposition, of being in many different locations at the same time. And that gives rise to all sorts of other things that I think are out there in the public domain, things like entanglement, the effect that Schrödinger talked about a lot, how quantum systems jointly can be in a superposition in a way that they're super correlated to one another. So there are all sorts of interesting phenomena, but they can all be explained through this property of being in many states at the same time.
Yeah, exactly. Well, and the idea also that the superposition state and how it can be perceived in multiple different ways, that gives rise to the idea of the observer.
Yes.
But a lot of times, when people who are not physicists are thinking about an observer, they think of it as a person. And that's not what an observer means in quantum mechanics. And I think that ambiguity causes a lot of confusion for people.
I think you're absolutely right. And I love the fact that you are stressing this right at the beginning of the discussion, because it leads to all sorts of statements that really go well beyond physics. And in fact, they have no support in physics at all. Statements like, if you really observe something, you can change your reality. If you focus on something, you can really make it happen, and things like that. Nothing like that exists in quantum mechanics. What does exist is simply, again, going back to Schrödinger, is that when you make an observation, and you're absolutely right to emphasize that an observer could be any other physical system. An observation doesn't need to involve human beings at all. In fact, it doesn't have to be a computer at all. It doesn't have to be as sophisticated as what we would call a computer. It could be simply an atom being observed by another atom. And so what happens during the observation is that the states of these atoms become entangled in Schrödinger's language, which means that for every position of one of these atoms, there is a corresponding position of the other atom. So they're somehow locked in this perfect correlation that their positions perfectly mirror one another. And that's where the measurement stops as far as a quantum physicist is concerned. You would say, I've now demonstrated that one of these atoms has measured another one. Now, of course, you can, and ultimately a physicist does get involved in confirming this, which means that you will now measure one of these atoms. And what will happen is that you will see only one of these positions manifest itself. And this is the property that I think causes many people to speculate and to become confused, because quantum physics does not tell us, and in fact, it cannot tell us in advance which of these outcomes you will see when you observe a quantum system. So this is something that's called the Heisenberg uncertainty principle, which means that if you're in a position, in a superposition of different locations, but you insist on asking what location is the system at, at a given time, you will only get randomly one of these possible locations. And all we can calculate is the probability to obtain that. So that's what quantum mechanics gives us. So if you repeat the same measurement many times and you get an expected value, then that's the value that quantum mechanics predicts. But each individual measurement, if you like, is, as far as quantum formalism is concerned, and as far as all the experiments are concerned, really random. You cannot predict this outcome. And so that's what's interesting. And I kind of developed this in my writings. What does this really mean for our reality? What kind of reality is that? And I think, but that's the crux of the question.
Yeah. Well, and it's also, it appears to be random, but whether it actually is not known at the present moment.
Absolutely. And that's another excellent point, that in fact, when we talk about two atoms, it's not random at all. The state that you get between two atoms when you make it so that through interaction, one of them measures the other atom, is a completely deterministic state. It's a well-defined state. It's an entangled state, admittedly, so it doesn't have any classical counterparts. And Schrödinger called entanglement the characteristic trait. It's really the trait of quantum mechanics that doesn't exist in any Newtonian classical physics. But nevertheless, there is nothing random about that state at all. The state is deterministic. And so that's what's interesting, that if you treat everything quantum mechanically, at the highest level, at the level of including everything into your consideration, you do recover determinism. And that's fascinating, that at the highest level, it's deterministic, but at the level of these individual interactions and observations, it looks random. So this is, in fact, what most of our research is about, to confirm this in more and more complicated scenarios.
Yeah, and that non-randomness, though, or indeterminacy, like that is ultimately, in your view, and if I'm summarizing it correctly here, is, you're saying that you're rejecting this idea that the measurement is creating many realities, or it is rather a copying of the state to the local classical object, if you will.
Yes, that's right.
From its observational standpoint.
That's right. And I think the only consistent treatment, and you are right, obviously, physics is a very open-ended enterprise, and our story may well change with the next revolution in physics. And in fact, my latest book is talking exactly about that I'm trying to anticipate which experiments we should be doing to probe and go beyond the current level of description. But the statement is that if you treat everything quantum mechanically, and this includes, the system you're observing, the apparatus you're using, if you like to use other computers, humans as observers, all of that is fine, so long as it's included consistently into this formalism. And if you do that, then you will not get any paradoxes in quantum mechanics. Is a perfectly consistent account, much like classic. It is different to classical physics, but it's consistent in the same way that classical physics is consistent. Of course, it may be proven wrong ultimately, that it's not the ultimate description, but that doesn't mean that it's not useful in its own domain, which is the current domain. After all, we've had 120 years of experimentation and not a single deviation from quantum mechanics. So I think that gives us a lot of confidence that it will be certainly true at a certain level of generality.
Yeah. Well, and basically, as you're framing it in the book here, that well, I guess let me step back. So the challenge that the quantum mechanics has had in quantum physics in extrapolating classicality from that is that because these objects are so small and the things that we have to measure them are so big in comparison, it's it's like trying to say, well, I'm going to measure how a tennis ball behaves by smashing a bowling ball into it. And
Yes.
that there's fundamental limitations on how you can do that. And so the instrumentality is really what has been our challenge in terms of extrapolating further from
Quantum mechanics as
Yes,
originally
extremely.
defined.
You're right. You're right. And I think the major stumbling when we discuss, for instance, these outstanding questions, as I do, gravity. You know, what happens with gravity? It's the only outstanding force that we haven't managed somehow to quantize. We don't really understand what it means to quantize gravity. And while many people would say that there are lots of mathematical problems with these kind of theories, that it leads to all sorts of infinities, nonsensical probabilities, negative probabilities, and things like that, the real big problem here is that we don't have a single experiment to give us any clues as to what we should be doing in this direction. And it's precisely because of what you said. This is a very challenging domain, and controlling systems in a fully quantum mechanical way to stay in these superpositions while making gravity relevant is a huge challenge. And we are probably at least 5 to 10 years away from being able to probe that, but we're getting closer, which is exciting to a physicist.
Yeah. Well, and then there's also, as you're saying in the book, that there's the challenge of the conceptualization of
Yes.
how quantum mechanics is the dominant perception. So, because of the instrumentality challenges, a lot of the discussion, perhaps most of it, is tending to be philosophical oriented
Yes.
rather than empirical oriented. And then
Yes.
further add upon that is the challenge that the Copenhagen interpretation is so dominant. But if you could maybe kind of unpeel that a bit for the audience here.
Yes, I think I can explain. So that's right. So Copenhagen interpretation is really due to Niels Bohr. I guess he was from Copenhagen, and the question, the way that he tried to understand quantum mechanics, and I think this evolved into an interpretation, and some of the early practitioners did subscribe to that. So people like Heisenberg is often quoted as being a member of Copenhagen School of Thought, but it's not clear. If you really read Heisenberg, I think you will see many differences with Bohr. So I think it's probably fair to say no two physicists really agree with each other on any of these aspects. But this interpretation of quantum mechanics emphasizes the notion of complementarity. So it takes this idea from classical mechanics that you either get particles or you have waves. And in classical mechanics, particles and waves were described by two completely different theories. We had Newton's theories for particle, and we had Maxwell's equations for waves, for electromagnetic waves. And for about 50 years or longer, they peacefully coexisted in this way. But then when with some of the early quantum experiments, people realized that sometimes quantum objects can behave like particles, and they almost fully comply with Newtonian description. And sometimes they behave like waves. And in fact, you can almost use equations that look remarkably like Maxwell's equations. After all, Schrödinger's equation is a wave equation as well. They behave like waves. They can interfere. If you have two slits, then these particles can really go through both of these slits at the same time and produce interference fringes like normal waves of light or water or any other waves would do. And so Niels Bohr thought that the main message of quantum mechanics, and this is where it becomes a bit mystical, and I think this is what promoted some of these views that at least as far as I'm concerned, go well beyond anything that quantum mechanics is really telling us. The mysticism there is simply, how does a quantum object know whether it should manifest itself as a particle or a wave? And then Niels Bohr would say, well, that's to do with the observer. That's how the observer comes into the Copenhagen and becomes kind of central to this interpretation. So Niels Bohr would say, if the observer chooses to witness the wave nature of the object, then the object will behave like a wave. And if the observer chooses to manifest the particle nature, to set up the experiment in that way, then the object will manifest itself as a particle. And you've got many unanswered questions here, which people immediately ask themselves. For instance, when you have a double slit experiment, if you close one of the slits, then the particle will only go through the open slit. It will really behave like a classical particle. But if you open the other slit, then suddenly each particle at a time seems to be able to go through both of these slits at the same time and produces an interference like a wave. So then the question automatically arises, how does the particle going through one slit know if the other slit is open or not? How does the particle know that at that moment it should become a wave? And this sounds extremely mysterious and mystical. It seems as though quantum objects have a superpower there. They can non-locally. This is something that Einstein, of course, disliked very much, and he kept complaining that he couldn't.
No, and even Schrödinger himself.
Even Schrödinger, in fact, indeed,
Yeah.
Schrödinger was very much against this picture of reality. So somehow it adds these mystical properties to particles, and at the same time, it suggests that it's all about observers. If I, as an observer, decide to witness a wave-like property of these particles, then I can set up the experiment in the wave-like way. And otherwise, if I monitor the particle continuously and I keep asking the particle, where are you now? I will get a sequence of locations much like a path, like a trajectory in Newtonian mechanics. And so to me, this interpretation, it happens to be the dominant interpretation simply because it's very pragmatic and it's frequently extremely easy to work with in terms of calculating the outcomes for given experimental setups. But if you want to understand what's going on, it seems to me it's not the right way to go. Actually, Dirac, by the way, Dirac had a fantastic statement about it along very similar lines. He said Copenhagen interpretation is good if you need to pass the quantum exam as an undergraduate at Cambridge, but actually if you want to know what's going on and understand quantum mechanics, it's certainly not sufficient. And I think that's where we are. That's why the interpretation has become dominant. But it seems to me less and less so with the recent experimental progress. The fact that we can now prepare larger and larger systems in this superposition of many different states at the same time seems to actually suggest that all of these extra systems, observers, anything we include into this, should also be treated quantum mechanically. They should not be treated any differently to any other physical object. And of course, we haven't really done experiment at that level to test this, but it seems to me that the right way to think about it is not to draw an artificial division between the observers and the observed. And in fact, any paradox, when you hear people saying quantum mechanics is paradoxical, here is yet another paradoxical and counterintuitive feature, all of this, in my view, comes from the fact that we are introducing these arbitrary observers that are completely unnecessary into the picture.
Yeah. Well, and that does go to the Schrödinger's famous cat example. Like he wasn't using that as an illustration of the paradoxicality. He was using it as to say, this is an absurd belief. You shouldn't think this. And yet it's like people took the opposite meaning from what he was doing with that.
Yes, I think so. Yeah, he was advocating, and I think I try to communicate quantum mechanics in that way, that you should really think about every particle as being part of an underlying field, of a wave that corresponds to this particle. And rather than thinking about these abrupt, sudden quantum jumps, where when you observe something, the state changes in a discontinuous fashion, something unexpected happens, and all of this, you should simply think of one wave entangling itself to another wave. And the joint state that's formed is a state that's perfectly well described by quantum mechanics. And there shouldn't be anything paradoxical about it. And I think if you read Schrödinger's, this is possibly even his last set of lectures, I think maybe a year or two before he died in the early 50s in Dublin. He does actually talk about this as his ultimate kind of realization, and that's what quantum mechanics is all about. And you are right that it's radically different from how we even teach quantum mechanics. If you pick up a random textbook, it will probably follow some version of Copenhagen. Actually, it will not be talking about it the way Schrödinger thought about it.
Yeah, it's an unfortunate irony.
Very unfortunate.
Yeah, and so but still, because of the well, frankly, the dominance of Copenhagen, it has in a lot of ways, in my view, kind of been a it's almost like it's like a god of the gaps in physics.
Yes,
that's almost what it is, and so it can explain something, but it doesn't actually tell you why it exists or how it is.
Yes.
It just merely says, well, this is how it functions, appears to function to us at this moment, but it doesn't tell you anything.
No, it doesn't tell you anything
of how these things are. And like, that's what this book is about, really.
Yeah, that's what the book is about, what kind of reality we should be talking about. And what's interesting, actually, this is another common misconception, is that you eliminate all of these things like non-locality. People talk about entanglement in the way that you measure one of these particles, and suddenly a particle that's very far away mysteriously, automatically, suddenly, faster than the speed of light, if you like, jumps and assumes the same state. Actually, that's not really what's happening. And we know that nothing in quantum mechanics violates special relativity. So I think Einstein really didn't need to worry about this aspect of quantum mechanics, but it does assume that we should be thinking about quantum mechanics more like Schrödinger did. Think about these underlying quantum numbers pertaining to all of the systems, and then simply think about interactions that entangle all of these quantum systems with one another. And then everything happens continuously, everything is smooth, everything is local, nothing changes at a distance in an abrupt way. And again, this reinforces this message that all of these paradoxes, all of these seeming violation of other areas of physics like relativity, simply happen because we are following this Copenhagen story in which these observers have these almost superpowers to change abruptly states of quantum systems. And of course, this leads us to conclude certain things that sound contradictory. And in fact, they are contradictory. But nothing in our experiments so far has led to any contradiction. So surely that means that there is a different story. And that's why I think Schrödinger was much closer to that.
Yeah, well, and the way that I kind of think about it is, and maybe this is dead wrong, but that basically, there is an externality that exists, but we can only access it through a perception of it. And so when you interact with a quantum system, you're not changing the nature of the object, you are changing your percepted externality. You are creating a new one for yourself. It is not, so in other words, there's not many worlds that are being created. It is, you are creating a new perception for yourself. That's what is created.
Yes, I think there is only one world. It's just exactly what you're saying. It's just that the only consistent way to understand it at present is really to quantize everything. So there is one quantum. It's certainly not a classical world. We know that for a fact, and we've disproved that on all of these occasions. But I think it's more appropriate to talk about one single quantum universe. Yes.
Yeah. Okay, great. Well, okay. So, and then, but because of the kind of conceptual and instrumental challenges that we've seen, quantum mechanics has seen, and a lot of people trying to advance, interpretations and ideas about it. And one of them who is this guy named Eric Weinstein, who is, I guess, a retired mathematician or something. Now he
Yes.
does, it seems to be only a podcaster now.
Yes.
But he released a paper a few years ago trying to claim that he had reconciled space time within a extra dimensional space. But on the other hand, a lot of his equations, he was just like, well, I don't have them, and I'm sorry. But
Yes.
he's very angry at people like you, Vlatko, for, according to him, he says you're suppressing him, you're censoring his ideas. But that doesn't seem to be what's happening here. It's mostly like, well, you said the dog ate your equations. That's what it looks like to me.
Yeah, to me too. I think you're right. I don't know Eric Weinstein myself, and he's not the only person, unfortunately, to make claims of that kind. Not at all. I think physics is a very open ended enterprise. It does happen to conventional physicists, of course, that you come up with an idea, you post it on archive, and then you get very disappointed that there is hardly any response. This happens. It happens to great ideas, by the way, that there is a 10, 20 year delay before someone actually realizes that there is something interesting there, or that an experiment could be done, and so on. But on the other hand, there are many dead ends. And I think, as you said, if you're a bit more mathematically minded, you will very easily think about all sorts of generalizations that you could go into. So, for instance, let me give you a very concrete example. Once you realize that quantum mechanics relies on complex numbers, so the imaginary numbers, the square root of -1, becomes crucial in quantum mechanics. You cannot describe these wave-like behaviors with real numbers only.
Well, it's because you're expanding degrees of freedom beyond the normal traditional spacing.
Exactly right. You're going into that space. But now, if you're a mathematician, and in fact, that's a perfectly legitimate thing to do for a mathematician, but you mustn't claim that that corresponds to reality then.
No, it's just a formalization. Yeah,
exactly right. Yes, that's right. And I think then you may say, well, why not use even more general entities? There are these quaternions, octonions. Why not use something that goes even beyond complex numbers? And of course, a physicist would say, well, we haven't had any need for that. It's not that we are conspiratorially blocking all of these beautiful mathematical abstractions. It's just that nature is telling us that what we have so far is sufficient. Of course, maybe one day these other formalisms, and we can never know whether they will become relevant, in the same way that we couldn't anticipate that their complex numbers would, they were discovered in the 17th century by some Italian mathematician who basically was solving cubic equations, and he found an interesting way of writing down some of these solutions. No one dreamt at that time, of course, that this would really correspond to some elements of reality. The same with general relativity, non-Euclidean geometry. All of these ideas ultimately were absorbed into physics. But I think to become upset that your mathematical generalizations are not taken seriously is a bit kind of immature, right? I mean, as a scientist, you should really understand how this works, and I think it's okay to speculate. But certainly you should not force your own ideas onto an experimental science, which of course, already contains methodology, how we find out what's needed, what's out there, or what's presumably out there, and things like that. So certainly there is no conspiracy within the scientific enterprise to block these ideas. In fact, we love crazy ideas. We love to hear that some ideas go beyond the current theory, because it gives us extra motivation to go in that direction and try to test these ideas. But they have to be well framed. You really have to make a conjecture. You have to stick your neck out, and you have to say concretely in what situation and what will happen that's different to what we already know. And that's extremely challenging, of course.
Well, and also you have to be able to specify experiments or other formalizations that could falsify your
Yes,
hypothesis. It's
absolutely.
not just to say this
Absolutely.
is my proof that it's true. You have to say, well, this is how it could be false, and here's how you would know.
Yes, absolutely. That's crucial. And like I said, we have, for instance, all sorts of collapse theories in quantum mechanics. And I think I would probably say that 90% of practitioners do not believe that quantum mechanics will collapse back to classical physics. But there are some prominent people like Roger Penrose, for instance, and many others, 10% probably of physicists, believe that there could be some domain, if the
and
objects,
they're really doing that in black holes, like that's their.
For instance,
exactly.
That's a big question in black holes. So there are many reasonable ideas there where things could go wrong. And I can tell you that all my experimental colleagues love this kind of even if they disagree with these speculations, they love them because frequently they tell how concretely to test whether these ideas are true or not. And we've ruled out many of these collapse theories, but there's certainly many other ones that are still outstanding. So they give us extra motivation to continue with difficult experiments.
Yeah, absolutely. And you really do, and it's I don't know how it is for you, but it's fun reading these papers of, well, here's how these quantum interactions within a black hole of this type, but it would be different from this other type. It's like these are not ideas that are suppressed. People enjoy reading them, don't they?
They enjoy reading them. It's okay to be speculative. It's even okay to say, I don't foresee an experiment even within next 50 years. That's fine. I mean, many ideas of the past are exactly of that kind, that it took a long time for us to get there to be able to test them. So we are extremely open to that. And as you say, it's part of the fun of being a theoretician.
Yeah, exactly.
Yeah.
And to that point though, on the experiments, so that is, one of that is the kind of the narrative sort of through line of your book here, is you're trying to say, okay, well, look, we're in some ways, because of our instrumental challenges and conceptualization problems, here's a way to kind of reset some of that and try to, experiment on how we could perceive if classicality is, fully derivable from quantum interaction.
Exactly right. And that's by no means clear. Like I said, we tested objects that are very large as far as an atomic physicist is concerned. So you have objects which contain, let's say, billions of atoms, but that's still nothing compared to even, let's say, a single biological cell. No one has put a biological cell into a superposition of two different locations. And in fact, many people doubt whether we will ever get there, simply because all sorts of other effects, noise from the environment and anything else, could prevent us from doing something like this. But that's exactly the direction we are taking, because what you want to do when you have a theory is you want to test it in domains where you think that it might fail. That's rather than just confirming it in one domain after another and doing kind of incremental stuff where you think that the theory will anyway be upheld. We try to really stretch it into exciting domains where there are reasonable arguments why it might fail there. And you already mentioned black holes. Anything to do with gravity is certainly in this domain. Living systems as well. We haven't really tested quantum mechanics much there. Even chemistry. Much of chemistry, actually.
Yeah, no, it's true. So within this idea, though, there is the term of the colloquial term, the quantum ghost. So what is that? And talk about how you want to, experiment with these things that we're talking.
Yes, that's a nice question, and I thought I really wanted to talk about it because not many people are thinking about it. It concerns, again, this very awkward marriage between relativity and quantum mechanics. So we have what's called quantum field theory. and it puts together special, not general, without gravity. So it's relativity without gravity together with quantum mechanics. And actually, some people would call this the most successful description of nature so far. You can call it the standard model, in fact. It really accounts for all the other three forces other than gravity. However, what's really interesting in this theory is that when you're talking about even basic electromagnetic interactions, if you have two charges and you want to explain how these two charges repel each other, if they're two electrons, two like charges, how they repel each other, or if they're oppositely charged, how they attract each other. The interesting thing is that in relativity, everything, every physical entity, every observable, if you like, every legitimate, relativistically legitimate entity has to have four components. So it's a little bit like three components of space, which is what Einstein realized in his first paper on this topic, and one component of time. So instead of thinking about space with three components separately from time, Einstein actually showed that you need to really think of them as one space-time, and that different observers perceive differently. Spatial units and temporal units, they only perceive one joint space-time in the same way. That's what's absolute, if you like, in the theory of relativity. So what's interesting for us is that when it comes to the electromagnetic field, we have the four components that we are talking about. But our standard treatment claims that two of these components can never be measured. They can never manifest themselves. In fact, when we do our calculations, we leave these two components out. However, they must be somewhere there to comply with relativity. You cannot completely forget them, which is why, as you mentioned, they're called ghosts. So they serve the purpose to make quantum mechanics comply with relativity, but then the claim is that they can never be directly measured. And this should kind of raise all sorts of alarm bells to a scientist, because you're thinking, wait a second, why do you need to postulate this in the first place if you really claim ultimately that you can never have any observable consequences? So something that I thought would be fun is to really try to think of an experiment where you could detect these ghosts. So these are simply two components of the electromagnetic field.
And what are these two components, if you can just kind of say that?
Yes, there are four components. Three of them look like spatial properties of the electromagnetic field. So they're telling you something about the strength of the electromagnetic field at different locations in space. And this fourth component, the temporal component, is telling you about how it behaves in time. So it very much mirrors the space-time of Einstein's, which was applied to the three components of space and one component of time. Here we are talking about three spatial components of the electromagnetic field, telling you about the strength of the electromagnetic field in the X, Y, and Z directions, if you like, in the three spatial directions. And then there is this fourth one, which is the temporal component, telling you how the electromagnetic field behaves in time. And suddenly, people say only two of these spatial components are relevant. There is another spatial component that's not directly measurable. And then there is this temporal component that's also not directly measurable. And they are known as ghosts because somehow the formalism needs to have them to comply with relativity. Otherwise, you would get instantaneous action at the distance. You could do things faster than the speed of light, and no one would want that. Obviously, none of our experiments are telling us that anything like this happens. So they're necessary for consistency, and yet somehow people say you can never detect particles of these extra components. You can never get a detector which would detect a photon coming from these extra ghost modes. And so I thought, and this is again being motivated by Schrödinger's thought experiments. It's very reminiscent what I have in mind of Schrödinger's cat experiment, where what I'd like to do is take a single electron, a single charge, put it in two different locations, and these are experiments that people do routinely. But now, if these ghost modes are real, if they're really out there, if they have these particles, photons that pertain to them, and if they're not just necessary for consistency, but if they're really out there, then our theory is telling us that they must somehow couple to this electron. They must become entangled to the electron through an interaction. And if you create this entangled state, then that's something that you could certainly experimentally verify. So what I have in mind is really one electron which is in two places at the same time. It becomes entangled to these ghost modes, and then I bring another electron in a superposition of different states, couple it to the first electron, and then ask what kind of outcomes I get. And actually the claim that I made in a couple of recent papers is that you could in principle detect this. No one has done this experiment, but I think these are exactly the adventurous experiments because they're challenging the current best description that we have of reality. And they're really asking these questions, can we go beyond that? And it would be very interesting. I'm actually betting on the fact that we could see the effects of disentanglement in much the same way that Schrödinger talked about entanglement in general. But to me, again, given that it would be more surprising not to see the effects, if we didn't see any effects, I think this would raise a serious question about our understanding of these fundamental interaction. The question is then, what does that really mean? How come that relativity is telling us one thing, whereas quantum mechanics doesn't seem to require these extra components?
Yeah. Well, and to that point, there are some theorists who argue that information is the fundamental nature of reality. So can we talk about that? But first, define what information is within this context, because again, that's another uncommon usage here, I think.
Yeah, very uncommon. I think the tricky bit is really the quantum side. So when it comes to classical information, first, I think it's the simpler one. I think when it comes to information, to define information, we follow Shannon in probably all sciences, not just in physics. Shannon wrote a couple of groundbreaking papers in the late 40s, and he really talked about communication. He was interested in the channel capacity. How much information can we communicate down a certain channel, and how do we specify this channel? And this was all about quantum information. So about classical information, and then I will talk about quantum. So what Shannon needed is, first, to be able to encode information, you need at least two distinguishable states of a physical system. So you need states which you can discriminate with certainty. Of course, in our computers, for instance, these states would be the electrical circuits which are either conducting current or not conducting current, and you can tell this zeros and ones. That's it. As soon as you have zeros and ones, going back to George Boole, of course, and Boolean logic, I think, you can encode information and you can talk about information. What you need, the second crucial concept, and you can now already see why I claim that it's much more appropriate to talk about quantum information. The second concept is that of probability. So Shannon said, if you tell me the probability to get the zero value of the bit and the one value of the bit, then I can calculate anything else. I can tell you the capacity of your communication in all sorts of scenarios. It's actually a universal way of talking about information. So you need bits of information. You need to be able to distinguish two states of each of these bits, and you need to know the probabilities for various strings of bits, zeros and ones. And so basically that's what Shannon did. And he showed that you can do anything. When it comes to computation, you can compute anything that's computable. You can reach any capacity that the channel allows with this. Now, the tricky bit with quantum mechanics, and I think that's where the difficulties arise, is that in quantum mechanics, you have, even with a single system, you have infinitely many ways of encoding classical information. So for instance, and this now is going to go back to Heisenberg's uncertainty. For instance, I could take positions of my object and two different positions are the values 0 and 1. If it's in one position, that's the logical 0. If it's in another position, it's the logical 1. However, you can also talk about superpositions. You can say, if it's in one superposition between these two places, that's logical value 0, if you like. If it's in another distinguishable superposition, I can call that logical value 1. And the tricky bit in quantum mechanics is that if you put these two together, then they do not constitute classical information. This is something that goes beyond classical information. So my colleague David Deutsch would call this super information. So he would say you have one property in which you can encode classical information, position. You have another property, let's say momentum, speed, in which you can encode classical information. But when you look at them together, because they cannot be simultaneously specified because of Heisenberg's uncertainty, they somehow transcend this concept of classical information. So actually a single quantum bit can exist in many, in fact, in infinitely many different states. Any superposition of the value 0 and the value 1 with any arbitrary weights between 0 and 1, you can have 75% 0, 25% 1, are allowed in quantum mechanics. And that's actually what's behind the strength of quantum communications and ultimately the quantum computers that we are building. Yeah. So it's in that sense that I talk about information.
Yeah, and that is the really fascinating and groundbreaking idea of quantum computing, because the problem with digital encoding and Boolean logic is that it cannot, when you look at a biological system, they don't operate under 0, 1. Yes. They operate under this probabilistic structure, yes. Especially with, like my current philosophical project is deriving, mindedness from cellular collectivity and perception and all of these, so in other words, like they have to agree on something's there, but what that something is and its there-ness is not 0, 1. No. And so like that's the beauty of using of trying to move computation to quantum state, is that you can have that kind of fuzzy, almost analogical logic.
Yes, you're putting it in a very beautiful way, actually, to the extent that we talked so far about how quantum mechanics changed Newtonian classical laws, but actually another way of putting it is exactly how you're putting it, that it changed the classical Boolean logic. It's not a binary logic anymore. The fact that you cannot say that something either is or isn't, but it could be in a superposition, in fact, in multitudes of different superpositions, forces us, and some people believe that that's how we should be thinking, forces us to change the logic, actually, to adapt, to basically use a different kind of logic to describe this kind of computation and communication.
Well, and that is also, what you are trying to why you're trying to back classicality out of it as yes. well, because that is the indeterminacy that we see from the measurement problem and the yes. observer problem, is that if you don't think of classical objects in the way that we have, then this mystery and this indeterminacy, this randomness, it disappears. Like that's your basic thesis.
That's my basic thesis, yes. And you're right. It's interesting that yes, it's all about consistency. If you mix, that's exactly how you're putting it. If you take a quantum system that obeys this fuzzy logic, and you couple it to a classical system that's deterministic and obeys Boolean logic, you're simply not going to be able to consistently even put them together, because the classical system does not speak quantum logic. It simply doesn't understand how it ought to respond to a quantum system. And again, we are back to Schrödinger. It's exactly Schrödinger's thought experiment, which says, wait a second, what's going to happen if I couple another system to a quantum system that's in a superposition? Well, it simply has to join that superposition, and that's it. That's your entangled state. And that's really the only consistent way of talking about it.
Yeah, and people are resisting that though, and I guess that's
People are
really what you're
resisting.
trying to do.
Yeah, that's what I'm trying to do, and people are resisting. Sometimes people even get angry because I guess it's very difficult to get rid of the Copenhagen kind of prejudice in many ways. And I think, like I said, we're all taught to think that way. Even in high school, the first time you meet quantum mechanics through Bohr's planetary model of the atomic structure and all of these things, all of these ideas creep in. And then certainly undergraduate physics, we're all taught that way. Most popular books are written that way, which actually amplifies this kind of mystical side of things. And no wonder it leads many people to actually conclude that it doesn't even make any sense. It can't be like this, it cannot be consistent. It must fail, it must collapse. But I'm arguing the other way, that if you really think of it quantum mechanically through and through, none of these paradoxes remain, actually.
Yeah. Well, and to that end, and the other way that you kind of bring that home is discussing that there are two types of numbers. So with the Q numbers and the C numbers. So
Yes.
Talk about that a little bit, if you will, please.
Yes, I think this takes us back exactly to Heisenberg's first paper, 1925. Last year was the year of quantum, right? Celebrating 100 years of his first paper. And that paper is taken as of course, there were many papers before that were already very close to doing to doing things this way. But the breakthrough there, the flash of kind of genius that he had, and it's really a magical paper to read, is that he said something quite revolutionary and it's again, it's not how we teach quantum mechanics. He said that the problems of classical physics are not at all the dynamical equations. So if you look at Newton's equation, force equals mass times acceleration, or if you look at Maxwell's classical equations, as far as Heisenberg was concerned, they're all fine. Dynamics is okay, and we don't need to modify it. But the revolutionary idea was that the entities that obey these dynamical equations, which we think of normally in classical physics as ordinary numbers. So you will say a particle is located 5 meters away from me, and in 3 seconds it will be 10 meters away, and then you can write the equation. And all of these are real numbers that enter these equations. Heisenberg had this idea that they should be upgraded into what Dirac later called quantum numbers. In fact, Heisenberg simply developed in that paper, he didn't know what they ought to be. Such objects already existed. They are called matrices. But Heisenberg, he was only 21, 22. I think he wasn't taught matrices at university. Matrices were already 50 years old then. I think they go back to Sylvester and people like Hamilton. Yeah. But they had not much use in physics. And I guess physicists were maybe not taught these things. And so he came up with these tables of numbers. So rather than needing just one real number, you need really lots of arrays and columns of real numbers, much like I think Schrödinger called them catalogs of information, which is a very colorful way of talking about matrices, one and the same thing. And so Heisenberg said, if you now admit that a position is actually one of these Q numbers, momentum is one of the Q numbers, energy, any classical property you can think of gets upgraded into a quantum number, a very complex array of numbers, then suddenly everything becomes clear, and he could apply that to spectroscopy. He could reproduce the spectra that were known at that time. And basically, people very quickly developed this idea later, applied it to a multitude of scenarios, and it became quickly clear that this is the way to think about it. So I find it beautiful because it illustrates this continuity of quantum physics with classical physics. It says you don't throw away everything from classical physics. Of course, many ideas from classical physics survive, and they're still legitimate. However, what you do need to do is upgrade certain concepts. And if you have the right idea of what it is that you need to upgrade, then suddenly everything falls into place, basically.
Yeah, and the other interesting thing about conceiving of it of physical objects in this processual way is that you eliminate actually all interaction problems, because that, like, within just like regular philosophy, there's this idea that how can things which have persistence and are objects, how can mental causality make them,
Right.
affect
Yes.
them? And basically, if everything is a process, then there is no challenge of interaction, because everything is a process interacting with the process, and ideas are just simply procedural variables inside of mind, which is itself a process, which is made of cellular entities, which are in the cell's quantum fields, made of quantum
I
fields.
like the picture that I very much subscribe to that. I don't like dualism or any kind of duality, right? That you make an artificial split between our mind or consciousness or whatever the brain does and what the rest of the world does. I think it's much nicer to think that there is a unity to nature, that we don't really need this artificial division. And you're right, this pops up even in quantum mechanics, right? That people would say, observers behave differently, living systems obey differently. But I think it's closer to reality to say that everything is the same. And you're right that many of these traditional problems disappear once you see it in this coherent fashion. I agree with that.
Yeah.
Of course, only time will tell. We haven't done the experiments yet at that level, but yes.
Yeah, but it does offer a consistency that if everything is simply procedural realization, then all the problems disappear. So many of the problems disappear.
Yes, I agree with that.
All right. Well, so besides this book, do you have any particular papers or people who want to kind of follow the more formal academic scientific papers that you want to recommend to people?
I think the best one that talks about quite a lot of these issues, and it may be a relatively friendly one to read, is a recent reviews of modern physics. So this is a magazine that publishes reviews that usually talk about a topical field of research, maybe that developed over the last 5 to 10 years. So I have a very nice review with my colleague Chiara Marletto. It was published last January, so exactly a year ago. And it talks about how methods of quantum information can be applied to test the quantum nature of the gravitational field. So I think this paper is probably, if anyone wants to read a bit more formal exposition, plus I think these reviews contain an extensive literature at the end. So I think we have over 200 or 300 references at the end of this review. So if anyone is interested to read this and see what people have been thinking about along these lines, that's probably the best place to look at.
Okay, awesome. And then you've also got a Substack that people can subscribe to as well if they want to.
Yes, I think my website, exactly. I think my website contains sections with different degrees of formality and difficulty, but I think I try to write my blogs in a very accessible way.
Okay, awesome. All right. Well, thanks for joining me today.
Thanks very much. Great pleasure.
All right, so that is the program for today. I appreciate you joining us for the conversation. And you can always get more if you go to theoryofchange.show, where we have the video, audio, and transcript of all the episodes. And of course, the links to the different papers and books that we talk about on all of the programs as well. And if you are a paid subscriber, you have unlimited access to the archives. And I thank you very much for your support. But we do also have free subscriptions as well. And you can get each of those at patreon.com/discoverflux, or you can go to theoryofchange.show so you can subscribe on Substack. And I thank you very much for doing that. And if you're watching on YouTube, make sure to click the like and subscribe button so you can get notified whenever there's a new episode. Thanks a lot for watching or listening, and I'll see you next time.